MIT engineers and researchers in South Korea have developed a sweat-proof electronic skin, a conformable sensor-embedded sticky patch that monitors a person's health without malfunctioning or peeling away, even when a wearer is perspiring. The patch is patterned with artificial sweat ducts similar to pores in human skin that the researchers etched through the material's ultra-thin layers. The pores perforate the patch in a kirigami-like pattern, similar to that of the Japanese paper cutting art. The design ensures that sweat can escape through the patch, preventing skin irritation and damage to embedded sensors. The kirigami design also helps the patch conform to human skin as it stretches and bends. This flexibility, paired with the material's ability to withstand sweat, enables it to monitor a person's health over long periods of time, which has not been possible with previous e-skin designs. The results published in the journal Science Advances are a step toward long-lasting smart skins that may track daily vitals or the progress on skin cancer and other conditions. The researchers have pioneered a technique called remote epitaxy, which involves growing ultra-thin, high-quality semiconductor films on wafers at high temperature and selectively peeling away the films, which they can then combine and stack to form sensors far thinner and more flexible than conventional wafer-based designs. Recently, their work drew the attention of the cosmetics company Amorphous, which was interested in developing thin wearable tape to continuously monitor changes in skin. The company struck up a collaboration with the researchers to fashion the group's flexible semiconducting films into something that could be worn over long periods of time. But the team soon came against a barrier that other e-skin designs have yet to clear, that is sweat. Most experimental designs embed sensors in sticky polymer-based materials that are not very breathable. Other designs made from woven nanofibers can let air through, but not sweat. If an e-skin were to work over the long term, it would have to be permeable to not just vapor, but also sweat. Sweat can accumulate between the e-skin and our skin, which could cause skin damage and sensor malfunctioning. So the researchers tried to address these two problems at the same time by allowing sweat to permeate through electronic skin. For design inspiration, the researchers looked to human sweat pores. They found that the diameter of the average pore measures about 100 microns and that pores are randomly distributed throughout skin. They ran some initial simulations to see how they might overlay and arrange artificial pores in a way that would not block actual pores in human skin. They started with a periodic pattern of holes, each about the size of an actual sweat pore. They found that if pores were spaced close together at a distance smaller than an average pore's diameter, the pattern as a whole would efficiently permeate sweat. But they also found that if the simple hole pattern were etched through a thin film, the film was not very stretchable and it broke easily when applied to skin. The researchers found they could increase the strength and flexibility of the hole pattern by cutting thin channels between each hole, creating a pattern of repeating dumbbells rather than simple holes that relaxed the strain rather than concentrating it in one place. This pattern, when etched into a material, created a stretchable, kirigami-like effect. The team fabricated an electronic skin from multiple functional layers, each which they etched with dumbbell patterned pores. The skin's layers comprise an ultra-thin semiconductor patterned array of sensors to monitor temperature, hydration, ultraviolet exposure, and mechanical strain. This sensor array is sandwiched between two thin protective films, all of which overlays a sticky polymer adhesive. The researchers tested the e-skin by sticking it to a volunteer's wrist and forehead. The volunteer wore the tape continuously over a week. Throughout this period, the new e-skin reliably measured his temperature, hydration levels, UV exposure, and pulse, even during sweat-inducing activities such as running on a treadmill for 30 minutes and consuming a spicy meal. The team's design also conformed to skin, sticking to the volunteer's forehead as he was asked to frown repeatedly while sweating profusely, compared with other e-skin designs that lacked sweat permeability and easily detached from the skin.